here. On YouTube, I've had some glitches with the videos that I have recorded. So ever since I lost one of the day's worth of videos, I have been simultaneously streaming and recording to my local device as a backup. And I've noticed that for some of the videos, the audio and the video gets out of sync. And it doesn't happen all the time, but it seems to happen to the ones that are recorded on the local machine. So I'm trying to use the ones on YouTube, but sometimes they have cut off short for no apparent reason also. So I'm going to try and do a better job of narrating what I'm looking at. That way, if you are listening to the video and you can hear the audio and it doesn't match, then hopefully you can still be able to follow along wherever we are in the handouts. So I'm going to try and work on that. But rather than pumpkins, we can talk about other stuff. So we have the tail end of example 5 to finish, and then hopefully get started on lecture 6 and example 6, extending the models that we were working with for ordinal items or binary items into ordinal items. So I want to start on 5. Let's see, that one's polytomous. That's not, that's example 6. Here we go. They look a lot the same. So we're in the binary IFA IRT models handout in example 5. We're looking at the fit of 7 binary items that are thought to measure one's ability to live independently as measured in 635 older adults. These are real data, so I don't have the data for you in the example 5 download folder, the zip folder, but I do have the full M+ output from all of the models that are fit so that you can see what that would have looked like. I've got the highlights in this handout here. So since we were starting, we finished off last time talking about differences in estimation and how you can assess fit or not under those differences. I thought that would be a good place just to revisit what you get in terms of full information output versus limited information output. So where we started, the very first models that we looked at for binary data, and this is sections 1 and 2, I believe, of the homework that you're working on. Homework 4, yes, homework 4, is asking you to fit full information maximum likelihood. So that's under analysis. So it's the same setup under both tabs here. Type equals general is something that you don't have to type. There's only a few instances in which it would be something other than general, so that's just an assumed default, but I have it here for completeness. It's estimator equals ML. That's the thing. So I'm on the first page of example 5 in the left-hand column. Estimator equals ML means that I am asking it to do full information marginal maximum likelihood. So it is using adaptive quadrature to come up with tryons of theta that it gives for each person in estimating the item parameters. And so at each iteration of the process, it's going to try on, by default, 15 different thetas for each dimension and come up with the likelihood of the data under that tryon of theta given the current iteration of the item parameters, and it's going to marginalize across all of the different tries. So it's using all of the original data. The plus side of this full information approach is that any missing responses are assumed missing at random. So that means conditionally random based on the other data that the person has given you that's in the model. So it's a less strict assumption than completely at random. So that's the plus side of this. The downside is that marginal maximum likelihood takes a lot longer to estimate if you have more than one trait. So for some of you who have multiple traits, this may not be possible, or it may take a very long time in your data that you're working with. And so I may need to help troubleshoot if you fall into that case. Question, what does marginalize mean again? It means going over theta. So it's the idea of if you're trying to compute the area under a curve, one way to do that is to divide up the curve into rectangles and to sum all of the rectangles. So that's the process that is being referred to as Gaussian quadrature, where Gaussian means the theta has a normal distribution. And so we're rectangling theta and aggregating over what the likelihood would be of the data under each possible try for what theta could be for each person. So because we've tried on all possible thetas, 15 per dimension is what the default is in M+, we don't have to know what theta would actually be for each person in order to get the likelihood. Because theta is not a parameter that is estimated for each person as part of the model. It's theta's mean, variance, and covariance with other thetas. That's the model parameter. Okay, does that help? So the marginal part refers to this numeric integration process. It isn't necessary to do that if you're assuming that your items are multivariate normally distributed. So this was not a thing in CFA, because if you have normal thetas and normal items together, that's a multivariate normal. This rectangling adaptive quadrature marginal maximum likelihood thing is necessary in any kind of model in which you have random effects that are normally distributed paired with some sort of conditional distribution that's not. So in, say, mixed effects models or multi-level models for non-normal outcomes, you see this same exact situation in terms of estimation and the difficulties that come with it. Okay, does that help definition-wise? Okay, so this is what we're asking it to do. Link equals logit is also a default, but I'm adding this here to make a point that you have a choice of logits or probits as you're scaling if you're estimating in maximum likelihood. Logits are easier to work with in that you can convert logits back into predicted probabilities very easily, and as well as odds if you want to do that. And so when we fit the model with these options, in terms of the fit that we get back, so the first column here on the left of page 2, this is it. That's all the fit statistics that you get. So you get the HO log likelihood. Remember, you are the HO. So that is the height of your model. In this case, we're fitting a 2PL. We're fitting a model in which each item gets its own A discrimination slope and its own B difficulty location. And the height of the data under that model of 14 parameters is given by the HO log likelihood. And what's not next to it that we used to see in CFA land? What's usually next to HO that's not here? Yeah, I'll take gestures. Yeah, H1, the perfect, all the data gets to be what it wants model is not here. It is not a thing in full information maximum like term. It is not a thing. What we have instead are these chi-square and likelihood ratio tests of how the observed model, how the observed categorical data, so the contingency table of all possible response patterns, matches the one that is generated by the model. So observed versus expected is sort of your classic idea of what goes into chi-square. And these things are basically worthless in most situations because we don't have enough people to fill up all the possible response patterns. So for instance, these tests are telling us that I have 113 degrees of freedom. Well, where the hell did that come from? That came from if I have 2 choices per item and I have 7 items, 2 to the 7th is 128. So that's how many possible response patterns that I have. I've estimated 7 loadings and 7 thresholds. Said differently, I've estimated 7 A's and 7 B's. And then minus 1 gets me to the degrees of freedom 113. So the 113 refers to the number of possible response patterns as sort of the beginning of degrees of freedom minus the number of parameters that you've estimated. So I would need at a minimum 128 times somewhere between 5 and 10 number of cases per cell to be able to, for these chi-squares to work. And then actually they give me an error message. Let me scroll back over to the other side. It tells me on the other side of the page that of the 630 cells in the indicator table, one of them was deleted in the calculation of the chi-square due to extreme values. And so it deletes cells that it doesn't have enough data to give you observed versus expected, which means that these models fit statistics are not comparable. So bottom line, disregard these chi-squares. They're not going to help you in most cases. All that you have in terms of the information that's given for model fit is relative fit. So you can use this HO log likelihood to test whether your model currently fits better than some other model, like 2PL versus 1PL or that kind of thing, but you can't use it to judge absolute fit. Absolute fit is tricky. It's not something that is easily summarized by one number. I'd say the most reasonable approach given what M plus gives you in particular is to ask for the Tech 10 output. That is available here on the output line. Tech 10 gives you chi-squares for every pair of items, and it compares the observed distribution to the expected distribution and gives you a significance test. So you can tell for a pair of items whether the model fits, and that can give you some indication as to whether there's like points of strain, the idea of local fit. But you have to look through all possible pairs for the chi-square test, and that gets to be very onerous. So in terms of assessing fit, it's much easier to do that in limited information estimation, and that's the new part that I haven't shown you yet that I wanted to show you today. So fit is hard to assess when you're using marginal maximum likelihood. And there's a chapter in your reading list, Medu Oliveras 2015, that discusses some of the newer measures of fit that are most likely implemented in other places. So any questions before I show you the other way to do this where you actually get fit info? You're going to like this much better. Okay, so scrolling, 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 stopping on page 6. So these are the same two models. I've got the 2PL code on the left and the 1PL code on the right with a few different lines. So I'll point out the differences here. Number one difference is right here on the analysis line. Rather than estimator equals ML, it's estimator equals WLSMB. Weighted least squares with a mean and variance correction. WLSMV is an M plus specific term. This estimation approach is known more generally as diagonally weighted least squares. You can phrase your model in two different ways. Using WLSMV, the way that I am recommending is parameterization equals theta. What that gives you is a scaling that corresponds to a probit link, where the residual variance of the pretend underlying distribution for your binary items is 1, and the model scale is in probits. So the model is now going to predict the z-score that corresponds with the probability rather than the logit. The model code itself looks exactly the same. So the by statement is how you define your factors. The thresholds are represented by the brackets. So binary items have only one threshold. When we get to ordinal items, you'll see that there's more than one threshold. And then the trait itself has its mean fixed to 0 in brackets and its variance fixed to 1 for identification. So to change your model estimation, the options under analysis are what you change. The model itself is the same. So to reiterate a point I was making at the end of last class, when people say in articles, I did CFA for categorical data and I used WLSMV instead of ML because I want to protect against non-normality, right? When they say that, they are talking simultaneously about a switch of estimation and a switch of model, but it's the switch of model that matters. So this approach, this idea of treating your items as categorical, that's the thing that matters, because that means that you are using a logit or probit link to make sure predicted outcome that is within the bounds of what it's supposed to be. And that translates into a nonlinear effect of theta instead of a linear effect of theta, which translates into reliability that depends on where you are in the trait. So all of those things go with the idea of treating it as categorical. Them mentioning the estimator just means that they're using limited information instead of full information. The downside of using limited information WLSMV is that any missing data are assumed missing completely at random. That's the downside. The upside is that there's no rectangling involved, because what this approach does is start from summarizing the data in a tetrachoric correlation matrix. You can think of it loosely as if you could have a correlation between the probits of the items instead of the original items. You can think of tetrachoric as sort of getting at that same idea. And so I had a question after class, can you use tetrachoric or polychoric correlations more generally? Absolutely. So if you're doing a paper and you want to talk about correlations between your study variables, and some of your study variables are binary variables, if you're going to use, say, logistic regression or probit regression to predict those binary variables, then rather than presenting Pearson correlations as your bivariate descriptive statistics, you would want to present tetrachoric correlations instead, because those are analogous to the idea that you're using a link function instead of a regular regression. So if you're doing, say, a general linear model, regression, or ANOVA, assuming normal residuals, a Pearson correlation matrix is a bivariate expression of that model. Whereas if you're going to do some sort of logistic or multinomial regression kind of thing, a tetrachoric or polychoric correlation is analogous to a bivariate expression of that model. So it's something you can use regardless of whether you're doing anything latent trait in that context. But this approach starts with that matrix. So it starts by summarizing all possible response patterns into a type of covariance matrix. So now we got H1 back, and we got fit back as a result. So we've got our answer key, and that's what makes fit possible. Question, is this a discipline-specific thing? Because people often present the correlations even with logistic regression. Is it because they don't know any better? Yes. I would almost guarantee it. You will have to go to a few extra lines of explanation as to what they are and probably give a reference, but I think it's worth it because it's a more consistent way of talking about bivariate relationships. So because we've got this tetrachoric correlation matrix as our answer key, now we can do CFA on it the same way as if we were doing it on a regular covariance matrix back in the day. So guess what? All of our fit stuff is back. Our friends are back. RMSEA is back. CFI is back. SRMR is back. The one thing that isn't back, though, there's no HO or H1 because there's no likelihood here. So you're not going to be able to do -2 log likelihood comparisons to test nested model differences because there is no likelihood in this approach. It's gone. It's not a thing. So I need to show you how to get M+ to do the model comparisons that you would want to do. It's an M+ specific thing. It's not a Excel calculator thing. And I'm assuming they have a package for Lavon that does this too. It's called Diff Test. That's what you want to look for. So in this example, if I want to test whether or not a 2PL model where all the items get different slopes fits better than a 1PL model where all the items share the same slope, the difference in the code I'm on page 6 of example 5. Still, the difference in the code lies in the by statements for each model. The word loading on the right-hand side is a label and a constraint. So all 7 loadings are going to take on the same value in the model on the right. So to be able to do a nested model comparison, to ask whether the 2PL fits better than the 1PL, here's what we got to do. Step 1, save the information from the model that has more parameters. So the bigger model goes first, order matters. The way that I'm going to do that is on the save data line. So on the left panel, in addition to asking it to save my factor scores like normal, I am asking it to add an option called Diff Test equals, and then after the equal sign is the name of a data set. You give it a name and a .dat extension, and it populates it with information related to the analysis. So 2PL is going to be the name of a data set that contains a summary of the results to be used in the nested model comparison. So bigger model comes first. The model that is nested within it, the model that has fewer parameters, then is going to take that saved information and incorporate it by adding that file onto the analysis line. So on the right-hand side, under the analysis option, in addition to specifying your estimator, parameterization, and convergence, there's a missing line on the left side that's present on the right side that's diff test equals the name of the previous data set that you saved. So it's going to bring that information in to do the comparisons. This is not something you can do by hand even if you wanted to. It's saving derivatives of stuff and doing math that I don't know if it's even something you could do in a closed form. The description of it is not very thorough in their documentation. So this is something you have to ask the computer to do.
Where does the summarized data come from? Does it spit that out and then save it, or is that something you do manually? You said it's the input file for diff test is a summary of your data?
No, it does it for you.
Okay.
So when you ask it to do WLSMV, the first thing that it's going to do is estimate a tetrachord correlation matrix from the data. It is then going to fit the IFA model parameters using that summary, and then it will generate a predicted matrix, and you can compare fit as the difference between the two, the same as you did in CFA. All of
So
that
in your
happens
code, where you have it labeled as 2pl.dat, did you have to tell it to save it under that name somewhere?
That is the name that I chose. So I chose the name 2PL as what the file is going to be called because that's what this model represents.
Okay, I thought that was something different, like you were embedding this as the code for it to refer to, but now I see what you're doing.
Nope, it's just giving it a name and then taking whatever I called it on the left and bringing that information into the analysis of the nested model.
Thank you.
Sure. So it's the same name in both places, but where that diff test equals goes, it goes on save data in the model with more parameters, and then it goes on analysis in the model with fewer. And once you do that, you will get, in addition to your regular testing, this new result, chi-square for difference testing is what they've labeled it as. That is your nested model comparison. So if the chi-square for difference testing is significant, there is a significant difference in fit between the two models. In this case, the degrees of freedom is 6 because you're comparing a model that started out with 7 loadings to a model that had 1 loading, a savings of 6. And the significant p-value means that going from 7 to 1 hurt the model. It's the same result that we found using full information maximum likelihood, where we did nested model comparisons using a likelihood ratio test, -2 log likelihood difference. So converging evidence that the 2BL fits better no matter how we're estimating the model parameters. In terms of the model parameters, what do you think? How good is my 2PL model? So highlighting the relevant things on page 6. What do you think? Thumbs up or thumbs down to my model? Oh, 2 thumbs up. That's even better than I was hoping for. Yeah. Question, is there a p-value? Can it only mean that it hurt the model? Yes, in the way that I'm talking about it. So in starting with the model that has more parameters, if you're comparing a model that has fewer, a significant p-value means going to fewer hurt it. And that order is the way this test has to be done. More to fewer. And yes, RMSEA of 0.068, CFI and TLI of 0.99, and SRMR of 0.04, all of these things would say this model is pretty good. So it fits well in an absolute sense. 2PL fits better than 1PL. 1PL fits worse than 2PL. And so in terms of the solution, it gives you the same parameters as in the full information maximum likelihood solution, but they're on a different scale. So the parameters from a logit model, which is what you get in full information maximum likelihood, are about 1.7 times bigger than the parameters from a probit model, which is what you are stuck with in WLSMV. So these are in probits. They are z-scores. So for instance, my factor loading for item 1, the loading estimate is 2.7. That means that for every 1 unit change in my theta factor, the predicted probit of my item response goes up by 2.7. Thresholds are still bullshit. They are the predicted probit of getting a 0 for someone with a trait score of 0. And what do I have to do to turn them into intercepts? Do you remember? Yeah. Change the sign. This is my change the sign sign. Yeah. So if I take the minus signs off of these thresholds, they become intercepts. And then they give me the predicted probit of a 1 response for a theta equals 0. Question regarding the direction of the comparison between 2PL and 1PL. Can we say the parameter is good because, can I say less parameters is good because of its parsimony? No. If the p-value is less than 0.05, having fewer parameters hurt the model fit. If the p-value is greater than 0.05, or whatever alpha that you set more generally, then that means that you can have fewer parameters without hurting fit. So yeah, this result would say, no, we need all 7 slopes. And then if we go to the other side, this is the IRT version of the model. So the discriminations are the same thing as the factor loadings. They tell you how good an item is at its difficulty location. And so the item difficulties, the B parameters, are given here. In terms of things by which to identify location on a trait, I find these to be far more useful. So I would find a way to work these into a publication because I think they're more intuitive. Even if they take a little bit of explanation, they give you the trait level at which you have a 50-50 probability. They tell you where the item is. For what kind of person is this item designed? That's what they tell you. And the fact that these are all negative, as we saw in the other solution, means that these are all really easy items. And we do not have information on people who have traits above 0. So we would need some harder items if we wanted to measure people of greater abilities. In terms of local fit, you're going to look for this matrix right here. Local fit in WLSMV is assessed in almost the exact same way as local fit in CFA. In CFA, we were looking for a normalized residual covariance matrix, where residual in that context meant the discrepancy between what the model says and what the data says, the correlations between items should be. This gives you that discrepancy in correlation directly. So these aren't z-scores. These are how far off the tetrachoric correlations are. And it looks like the worst one is a discrepancy in correlation of about 0.1. That's as bad as it gets. And most of these are 0 to the second decimal place. So that's where the overall quality of fit from the model is coming from. On the whole, the model is reproducing our estimated tetrachoric correlation matrix. The one that is predicted by the model is doing so reasonably well. And as I promised, here's some words. So the approach that I'm going to ask you to take with your own data in homework 5 is to start with WLSMV so that you can go through the process of checking fit, both local and global, and then when it goes to reporting the model parameters to switch into ML if possible so that you can be in the familiar logit metric and talk about the parameters in that scaling that's a little more intuitive. Plus ML is supposed to be a better version of the parameters because you're using all the original data. So that's going to be the plan for homework 5. All right. So questions on any of this or any of this you want to hear again?
Yes, there was one where I was typing as you were saying, and I think I may have typed the wrong one.
Okay.
For the full model, which the full model is the one that assumes missing at random, or is it the limited model? Which one's which? And if it's, I thought it was the limited.
Full information, maximum likelihood, any missing items are missing at random.
Yeah.
Conditional random is what that means. And the limited information is the one where it's assuming completely at random.
Okay, thank you.
And that is true of any limited information approach. If you start by summarizing information and you work with that summary, you don't know what went into the summary. Whereas all of the original responses or lack thereof go into the likelihood function if you're doing it in ML. So that's the one downside of WLSMV is with respect to missing data. And that's where if you're dealing with it in practice, you may want to consider multiple imputation to be able to have a missing at random mechanism instead of missing completely at random that's going to be more reasonable. Can I still get item or test information using WLSMV? Yes. So all the pictures that I made in terms of item characteristic curves, test information curves, and all that stuff, you can get out of WLSMV. By the way, in your homework 4, I made pictures for you because the Mac version of M+ doesn't make pictures for whatever reason, and I didn't want there to be different versions across different things that you guys are using for the pictures. So I made all the pictures that I'm asking about for you, and they're included in the download file. So you don't have to worry about that for homework 4. For your own data, if you are using M+ on a Mac, you'll need to temporarily use it on something else to be able to make your pictures. And that's something that I can help you with too. If push comes to shove, you can send me your stuff and I'll run it for you on my machine. I have already had to do that to help some people troubleshoot, so I'm willing to do that if need be. But yes, you can get all the same pictures either way. The model estimates are just in a different scale. Okay, other questions? Okay, you feeling like you can do this? It's not so bad. The logit is the tricky part. The coding is relatively straightforward. The good news is that all of the stuff for ordinal data is going to rely on these same mechanisms. Just an order of complexity higher because there's going to be more than one binary submodel for your ordinal data. So do you want to talk about that? Since most of you have ordinal data that you're playing with? Okay, so I'm going to close example 5 and pick up